All right, so thus far in our discussion of forces, we've talked about Newton's first two laws of motion. The first being that an object in motion has a tendency to stay in motion, and an object at rest has a tendency to stay at rest unless it is acted upon by an outside force. Okay, and basically the laws of motion, we've kind of talked about how we've described motion in terms of velocity, acceleration with respect to time, and how far it travels, its distance. So we've talked about motion, but we haven't talked about what sets things into motion, and that is forces. Okay, forces are what set things into motion. And yesterday we talked a little bit about how a force is proportional to its mass times acceleration, right? So if I have an object with a certain mass and I act on it with a certain amount of force, it should accelerate at a certain rate. Or if I accelerate a certain mass at if I accelerate a certain mass, it'll have a certain force, right? If I accelerate something at 2 meters per second and it weighs 100 kilograms, it's going to hit with 200 newtons of force, right? 2 times 100 equals 200 newtons. So, yesterday we basically just did some problems where we rearranged this simple formula to solve for either force, mass, or acceleration. On page 89 in the book, you'll look and see that exercise 3 does not give us an acceleration. It doesn't give us an acceleration, and so we're gonna in this video walk through that problem together. So if you would turn in your books to page 89 and grab a pencil and some paper and a calculator, we'll be able to go through this problem together. So the problem says that a race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. The car is uniformly accelerated the entire time. What is the net force applied to it? So it's asking us for a force, it's giving us a mass, but it's not giving us an acceleration, it's only giving us a means by which we can find acceleration. So, what equation have we used thus far that has both distance, right, like 40 meters is a distance, time, like 3 seconds is a time, and has acceleration in it? Well, if you recall, the equation d equals VIT plus 1/2 AT squared has time, it has acceleration, which is what we want to solve for, and it has distance. All right, but what about VI times t? Well, it says in the problem that the race car is starting from rest. So the initial velocity then would be 0, and 0 times t would just still be 0. So we're not concerned with that. We can just cross that out. Let's scribble it. It's gone. Who cares? All right, so our distance is 40 meters. Okay, and that equals 1/2 times a, and then our time, what is time? It says time is 3 seconds, so 3 squared would be 3 times 3, and 3 times 3 is 9. We can simplify this further. If we take 1/2 of 9, we would get 40 meters equals 4.5 times a. Okay? So now, if we take both sides divided by 4.5, 4.5 cancels out, and we're left with 8.88888 repeating. So that would round up to 8.9 what? It's an acceleration, right? 8.9 meters per second squared. All right, so we found our acceleration that we needed. Now let's go ahead and plug it back into this equation. I'll get a fresh sheet here. All right. So if F equals m times a, and we know our mass is 710 kilograms, and our acceleration is 8.9 meters per second squared. If we take those two values and multiply them together, we should get our force. Our force is 6.3 times 10 to the 3 newtons. Awesome. All right, so that's how you solve that equation, using our motion, using Newton's second law, right? The equation from Newton's second law, and using our distance formula from the previous chapters.